Okay, so after our conditions have been met, we can now construct a confidence interval for our population proportion P using this form. P hat plus or minus Z star times the square root of P hat multiplied by 1 minus P hat over N. Remember, this is our point estimate, this is our critical value, and this is our standard deviation or statistic. So let's go ahead, let's go through a practice problem. But before that, my advice is whenever you're going to go through a full inference problem, use some sort of step-by-step method, especially when you're first starting this, and especially if you're going to be taking the AP Stats exam, because when you go about it in a set way, you can be sure that you're going to get full credit on the free response problems, because this breaks down exactly what the graders are going to be looking for. So we're going to use a state, plan, do, conclude method. I didn't invent this method. I don't claim to have invented it, but I've had a lot of success having my students follow it. So let's say we have this problem where we have Jordan learned in her first grade social studies class that 70% of the Earth's surface was covered in water. And she, was wondering, is this really true? And asked her dad for help. So to investigate, he tossed an inflatable globe 2 or 50 times, being careful to spin it. And each time she caught it, he recorded where her right index finger was pointing. So essentially, he tossed it her 50 times and tried to record 50 different locations of where she was pointing to with her index finger. And out of those 50 tosses, 33 of the times, her finger was pointing to water. So we start with our statement. So what exactly are we trying to estimate? Well, our population parameter is going to be the true proportion P that is covered in water. And we're trying to estimate it with a 95% confidence level. Next, we're going to state our plan. So what type of inference method are we going to use? Well, we're going to use a one sample Z interval for P if the conditions are met. Now this may kind of seem weird at first, is why do you have to mention this? And you're going to learn actually other inference methods. You're going to learn one sample T interval, you're going to learn 2 sample intervals, you're going to learn something for chi-square distributions. You're going to learn there's going to be multiple inference methods, so you're going to have to be very strategic in which one you're going to use, so specify it here. So now let's check the conditions. So first let's check the random condition. And since he spun the globe to her 50 times, we can say that the 50 locations of the sample, were done at random. So that condition is met. 10% condition. Now, in this case, the sampling was actually done with replacement, so we actually don't have to check this one, because technically she could have, had her finger land on the same spot twice. She didn't point her finger in one spot and then say, okay, I'm not going to be able to land my finger on that spot again. No, it was done with replacement, so this is actually not necessary to check. Now, the large counts condition, we got to check if n times p hat and if n times 1 minus p hat are both at least 10. So our p hat, remember, is going to be our sample proportion. So out of the 50 tosses, 33 of them were landing on water, so our sample proportion would be 33 out of 50. Now, another way to think of this is the number of successes and failures. So first, if we just did it that way with our p hat being 33 over 50, we would have n times p hat is 50 times 33 over 50, and we would get 33. That's at least 10. And if we did n times 1 minus p hat, we would get 50 times 17 over 50. We would get 17. Now, the reason we call this the number of successes and failures condition as well is because these two numbers are going to add up to the sample size always. Because if 33 times she landed on water, then it means the other 17 times she didn't. So this basically would have 33 successes or 17 failures. So you're going to hear that thrown around. I use it a lot. So they're essentially the same thing. Okay, now we go to our calculation, our do step. So we're going to use our one sample z interval. So let's first rewrite it over here. I'm being careful not to give away the answer. We're going to use our p hat plus or minus z star times the square root of p hat times 1 minus p hat all over n. So let's first convert these into like decimals. So our p hat is going to be 33 over 50, which is going to be 0.66. So we're going to have 0.66 plus or minus our z star. Now, remember, our z star is our critical value, and we're trying to estimate this with 95% confidence. So we're essentially trying to find the z values on the normal curve where there's 2.5% to the left and 2.5% to the right. So if you were to use your calculator, and a quicker way to do this is to go to the inverse norm function. First go to distribution, the inverse norm, and you're going to enter the area to the left. So again, if we're having a 95% confidence interval, there's going to be 5% of the area left over. Since it's symmetrical, you're going to have 2.5% on each side, or 0.025 to one side. The next value we're going to enter is the mean. And since it's the standard normal curve, our mean is 0. And then we're going to enter the standard deviation, which is going to be 1. Close parentheses, and it's going to give us our z star value, but to the left, so it's approximately negative 1.96. Our z star value is always typically interpreted to be the positive value, so we're going to write 1.96 as our z star. And so this comes out to be this. Okay, just going through the basic math, and you work it out. And this is okay to use a calculator to do this on your stats exam. It's not about testing if you can do these type of calculations. It's about the concept. So you always will be allowed a calculator in every problem on your exam. So make sure you become very handy with it. So we're going to get approximately our interval to be 0.66 plus or minus 0.1313. So we're going to add 0.1313 to 0.66, and we're going to subtract 0.1313 from 0.66. And our left side will be about 0.529, and our right side will be about 0.791. So this is going to be our 95% confidence interval. So we're essentially going to say, as a conclusion, that we're about 95% confident that the true proportion P lies in this interval. And the claim was that P is 70%, or P is 0.7, because her teacher told her that 70% of the Earth's surface is covered in water. Now, 0.7 is in this interval. So since it's in this interval, we can say that, hey, it's reasonable that her teacher was right. It's a plausible value, we can say. It's reasonable to believe that the true value of P is 0.7 because it lies in our 95% confidence interval. Doesn't mean that it is for sure, but it just essentially means that we have reasonable enough proof to agree with her.